Hey guys, this is take 2 for the Math 1230 video on integration by parts. So this is section 7.1 in your textbook. Take 2 because the first take I think was the audio was too low, and I have a brand new microphone, hopefully better. Okay, in this section I'm going to refer to a particular method of integration by the acronym IBP, and it stands for integration by parts. Before getting to that new algorithm, I want to review integration. A review video of integration can be found prior to this one. So on the OWL page, directly to the left of where this one was posted, you can find these examples worked through taking the antiderivative of the cosine of 2x. You do this by substitution. X times the cos of x squared, you also do this one by substitution. So in this case, you'd let u equal x squared or let w equal x squared, depending on which letter you want to use. And for the next one, if you try the same thing, if you try to do substitution, check out the video if you want to see what happens. It doesn't work out well. You end up just replacing all the variable labels with a different label and have the exact same problem with a u instead of an x everywhere. And so it's not helpful to try substitution to solve this integral. So the method that you're about to see, learn, this method called integration by parts, gives you access to solving a different class of integrals, including the two that are presented here, the integral of ln of x and the integral of x times e to the x. After the lesson, I want you to come back to these two, try them on your own, and I'm not going to post a solution because you can check. You can check by taking the derivative of the result and making sure you get back what you're taking the antiderivative of in the first place. Okay. Also in the previous video, the one to the left of this one on the OWL page, you can see a review of derivatives with the product rule. So in the example A here, we have a function x and a function ln of x multiplied together. When we take the derivative of that product, we have to do a product rule. And then there's a separate derivative of the term off to the right that's independent of that first term because it's separated by a plus sign or a minus sign. In the example below, example B, there's also a product rule in the taking the derivative of the product x times the sine of x. So the first part of the product would be x, the second part of the product would be sine of x. So in my notation in my class, I would say a is equal to x and b is equal to sine of x, and then do ab prime plus ba prime for the product rule derivative for that first part, and then a separate derivative for the derivative of cosine. And as you'll see on that video, the expressions simplify in a nice way, and what they simplify to, in the first instance, answers one of the questions earlier in this video, and the second instance answers a question from later on in the video. As another reminder, the distinction between derivatives and antiderivatives, or the relationship between derivatives and antiderivatives, is that they are kind of, but not almost, things that you can consider inverse operations of each other. If you take the derivative of sine of x, you get cosine of x. If you take the antiderivative of the cosine of x, you get the sine of x. So it's one operation takes you from left to right, the other operation takes you back. There's a little bit of a wrinkle here that there should be a plus c. When we take the antiderivative of cosine of x, we get sine of x plus a constant, plus that constant integration, which we call a plus c. I've not written any of those here, but they are there. Okay, and the last thing that's inside the video that's posted to the left of this one, the review or preview video, is this question, multiple choice problem. Not knowing this method of integration by parts, but given some choices. You're asked, what is the antiderivative of x times the sine of x? And it has to be one of these three options. What you do to check which one works is to take the derivative of each one, using the product rule wherever it's appropriate. One of them will match, and the other two will not match. And by match, I mean when you take the derivative of the correct expression, you'll get x times the sine of x. So it's d by dx of which one equals x sine of x. And to see the full solution to that, check the video. For this video, what's new is this method called integration by parts. And in order to get access to this method, we have to go back to the product rule and use it in a different way, explore it in a new way. I know that typically in product rules, for the product of functions, we have f and g. So we would say d by dx of f times g is fg prime plus gf prime. Or you'd use a and b, so the derivative of a times b is ab prime plus ba prime. But for historical reasons, and so that we want to match up with everybody else is writing, whatever everybody else is doing, and this is what they do. This is how mathematicians would write the product rule in preparation for using integration by parts, is we would say the two functions that are multiplied together in the product will be labeled as u and v. And then if we take the derivative with that notation, so the derivative of u times v, we're taking an x derivative, considering u and v as functions of the x variable, then the derivative will be uv prime plus vu prime. And I'm going to rewrite v prime as dv by dx and u prime as du by dx to indicate that we're taking the derivative with respect to the x variable. Small change in the function divided by a small change in the x coordinate. Next step. So I'm going to write down that step again. D by dx of u times v equals u times dv by dx plus v times du by dx. And then do a step, kind of two things in one as one type of a step. What I'm going to do is I'm going to integrate both sides. Take the antiderivative of the left side and the antiderivative of the left side and an antiderivative of the right side. So I'm just going to make a copy of those. I'll put some stuff there to go along with it. U times dv by dx plus v times du by dx. Okay, and then I'm going to integrate both sides with respect to the x variable. Okay, so the dx is needed because we're integrating with respect to the x variable. On the left-hand side, we're taking the antiderivative of the derivative. So this might look dumb in what I'm about to write, but hopefully it's instructive. What is the antiderivative of the derivative of x squared? Well, we can do that one by taking the derivative of x squared. The derivative of x squared, so doing the inner operation first. Derivative of x squared is 2x. And now we take the antiderivative of 2x, which is x squared. So in general, if I said, what is, so that's a big OK. Imagine replacing that with an x to the power of 3. The derivative of x to the power of 3 is 3x squared, and the antiderivative of 3x squared is going to be x to the 3. Okay, so you put any function there, what's going to happen is the following. So in general, the antiderivative of the derivative of some function, which I'll call f of x, is going to be f of x plus c, because the derivative does an operation to the function. The antiderivative is a different operation. It undoes what the derivative did. You get a little bit of extra, you get a plus c, as we always get with indefinite integrals. I'm going to apply that logic to the left-hand side. We're taking the antiderivative of the derivative of u times v, so we're going to get u times v. Now on the right-hand side, I'm going to split up the integral of u dv by dx with respect to x plus integral of v du by dx integrated with respect to x. And the horrible things that we were doing without really thinking too carefully about them, we just did them in the section on integrating by substitution, where we were taking du by dx and cross multiplying and kind of manipulating that expression, tearing it apart. We're going to do something even worse. I'm going to cancel the dx and the dx, the dx and the dx. And we get an expression that doesn't look, maybe it doesn't look particularly meaningful. Like, what are you going to do with this? It's like a so what moment for now. We get this statement that says u times v is equal to the antiderivative of u with respect to v plus the antiderivative of v with respect to u. So it's a weird looking and perhaps not useful expression. I'm going to modify it in one simple way. I'm going to subtract v du from both sides. So uv minus the integral of v du is equal to integral of u dv. Just rearranging. Okay, and then that's the statement, but I like writing things left to right. So the thing on the right there, I'm going to put on the left-hand side, integral of u dv is equal to uv minus integral of v du. Okay, and it's a special formula. That's the IBP formula. And the logic, or the reasoning, is as follows. The one on the left would be I'll call it a hard integral, the hard integral that we start with. The u times v is some function. So a function gets spit out, and then the v du, that's a new integral that might be easier to solve. So it's like a trade. You have a problem that you don't know how to do, so you trade it for another problem, and maybe you can solve that one. I'll show you how it works. Okay, so first example, find the antiderivative of x times the cosine of x. Substitution won't get you very far. So this is what I'll try. I'll try using the integration by parts formula. Use integration by parts. IBP. To use this method, we're going to say that this expression here is equivalent to u times dv. Where u is equal to part of x times the cos of x times dx. But the dx is never going to be part of u, it's always going to be part of dv, is equal to the rest of x times the cosine of x times dx. So this is the structure that we will always have when we do integration by parts problems. U will be equal to part of the integrand, so either x or cosine of x in this case, and dv will equal everything else that we did not include inside u, and then that multiplied by dx, which indicates just integration variable. Okay, our formula for IBP is that we have integral of u dv equals u times v minus integral of v times du. To use this formula, we need all of the ingredients in it. I'm going to split the problem into two cases. Because we really have a choice here. So I'll call this attempt 1. In attempt 1, I'll let u equal cosine of x. Now, dv has to be everything else in the expression, which in this case is just x, multiplied by dx. So on the left-hand side, I have integral of x times the cosine of x dx is equal to u times v. So u I can put in cosine of x. I leave a space for v minus integral of v du. I have to leave a space for those. Okay, so this cosine of x was the u. This box here is for v. This piece here is also going to be v. And this piece here is going to be the du. Those are v's, not check marks. Okay. Now we need to find what those pieces are. So for the u piece, we can take the derivative of that. Du by dx is negative sine of x. That means du is equal to negative sine of x times the times dx. Am I doing negative sine of x times dx? So I'm going to plug that in the box that's slightly too small. Negative sine of x times dx. Now we need to get v to plug into those two pieces. To get v, we're going to take the antiderivative of both sides of the expression. There's a 1 that's hiding there. dv is the same thing as 1 times dv equals integral of x dx. Okay, the antiderivative of 1 with respect to v is just v. The antiderivative of x with respect to x is 1/2 x squared using the anti-power rule. There is a plus c, but we'll just take care of the plus c later. I'm not going to embed it at this stage. We just needed it once at the end, and that's what we'll do. So now I'm going to embed, put the v in the spot where things appeared inside the formula. Okay, next step is I'm going to clean things up. Constants usually go in front of the expression. Polynomial terms, algebraic terms go next. Then trig functions and logs and exponentials battle it out to see who goes next inside standard form expressions. So that's how it would look in a textbook. And then the next piece, we have two minus signs. They're going to cancel and make a plus sign. So plus integral. And we can bring the 1/2 out as well. Constants can be a factor out of integrals. So 1/2 integral x squared times the sine of x dx. And then we would need to continue from here. Okay, and I'm going to tell you that this is a sign of something gone wrong, not a mistake in terms of the mathematics that's been done, but a mistake in terms of the strategy that was used. The expression began as x times the cosine of x, and now the new integral that we have is x squared times the sine of x. So this is arguably a worse expression. It has a higher power of x on it. We're not getting closer to an answer, we're getting further away. We replaced it with a harder problem. Okay, in method 2, or attempt number 2. So thinking back to the step where I said u is equal to cosine of x, so everything else is going to be x dx. Well, we're going to make the other choice. Instead of letting u equal cosine of x, we're going to let u equal x. So attempt 2. So I'll let u equal x. So everything has to be reconstructed when we take u and multiply it by dv. So dv must contain the cosine of x and the dx. Our expression was x times the cosine of x dx equals, using the formula uv minus integral of v du. I'm going to write it down again because it's a little bit high up above. I want to have it right here where we're going to use it. Okay, and then put in the components. U, we said, was x. V we'll have to find. I'll leave a space for it. Minus integral. I'll leave a space for v and a space for the du. I don't know why I have the brackets all shaped like that. Put square brackets for everything, I guess. Doesn't matter what brackets you use. Okay. Now, if u is equal to x, then du by dx is 1. So du is equal to dx when we cross multiply. So there's that. If v is equal to cosine of x, or dv is equal to cosine of x, we can integrate both sides. The integral of 1 with respect to v is equal to the integral of cos of x with respect to x. So we get v equals, the antiderivative of cos is positive sine. So that can go in those two locations. I think in the first version of the video I made, I had that screwed up. Almost certain something was wrong there. I put in the wrong thing. Okay, so we have x times the sine of x minus integral of sine of x. Just getting rid of the colors and getting rid of the extraneous brackets. So this is what has been accomplished. We took the x times the cosine of x and have replaced it with an integral of just sine of x, which is simple. It's something that we can quote by memory. The antiderivative of sine is negative cosine. And now we can tack on the plus c and clean up the negative times negative is positive. So x times the sine of x plus the cosine of x plus c. And as with all antiderivative problems, these are like custom built for you to check your answer. Check if d by dx, so that expression at the end, d by dx of x times the sine of x plus the cosine of x plus c. If you take the derivative of that, all that stuff, if we did everything right, the answer will be x times the cosine of x. Go through a product rule. So this is quick. Go through a product rule. A times b prime, so x times the cosine of x plus b times a prime plus sine of x. So that's the product rule for those two terms. And then the derivative of cos is negative sine of x. The derivative of c is 0 since c is a constant. And we get the sine of x and the negative sine of x canceling. We get what we need, x times the cosine of x as needed. this is not particular to integration by parts. This check is something you can always do when you integrate. So I think I'll stop the video here. The rest of the video is more examples like this. The original one with the low volume, I'm going to try to boost it, but I at least wanted to redo this one with better audio and me not so tired. Like I did that one, I don't know what time in the morning, at 4 o'clock in the morning or something, and I think it came through that way in the audio. It wasn't just the microphone. I think it was me too. Take care, guys.